Well, up to this point, you guys, we've studied how to find the derivative of a function, how to use it to solve, a wide range of problems. But there's a lot of other problems that require us to recover a function from a derivative. For example, in like physics, you have an acceleration of an object, and you might be given the acceleration of an object, and we could use it to find the initial height, right? We could use it to find the velocity and so on. And so you want to actually go backwards, if you will, from the derivative. And so we'll see that these antiderivatives or integrals are this link connecting these two major elements of calculus, the derivatives and definite integrals. Okay. So let's talk for a minute. Let's suppose let's say they ask us find a function whose derivative is 3x squared. And hopefully you would say, what would the original function be then? X cubed. Good. X cubed would work, right? X cubed would work. Can you think of another function whose derivative is 3x squared?
Anything where it has a constant at the end.
Good. So x cubed plus 2, that derivative is also 3x squared. You could also have like x cubed minus 1, whatever it may be, anything, as was mentioned, anything with a constant, its derivative would be 3x squared. So let's attach a little notation to this. So we're going to go backwards. We're going to say, all right, what's the antiderivative of x? I'm sorry, we're finding the antiderivative of 3x squared, right? Because we're trying to find the function whose derivative is 3x squared. And so we just would go backwards with these rules. And so the 3, we'd say the 3 would stay there, but instead of, with the derivative, we'd have the power rule n x to the n minus 1. Here we'll have x to the n plus 1 all over n plus 1. And then we just attach a constant to the end. So this just ends up being 3x to the third all over 3 plus a constant. In other words, x to the third plus the constant is our original function. That's the function whose derivative is 3x squared. And that capital C just means it can be any constant, right? It could be 0, it could be 2, -1, whatever it is, that its derivative is 3x squared. Okay? So that's our power rule for antiderivatives. Let's do another one with that same power rule. Let's take the antiderivative of x to the fourth. And the dx, by the way, so here's the integral or the antiderivative. Antiderivative sign. And this just says with respect to x. So I'm taking the antiderivative with respect to x. That's that dx right there. Okay. And so in this case, we're looking for who's the function whose derivative is x to the fourth, right? So let's do it. But let's actually use the rule over here, right? So I go x to the 4 plus 1 all over that 4 plus 1 and plus a constant. So x to the fifth over 5 plus a constant would be our answer. In other words, if I take this derivative of the constant 0, see how we get back to x to the fourth? Right? So we're just going backwards. That's all we're doing. So that's the way you can check it. At the end, take the derivative, you should end up with whatever you're taking the integral of or taking the antiderivative of. So here's a bunch of rules, formulas, and their properties. Okay. Let's do a few here. Let's do this one right there. The integral of a constant with respect to x is constant stays there, and then you throw an x on it, plus c. In other words, if I take that derivative of 7x, plus constant, derivative of 7x is 7, right? Of course, derivative of constant is 0. Our third rule down here, notice that I can put that k out front and then run the integral on that. Okay. So, for example, the integral of 7x squared. I could put the 7 out front, and now I run the power rule for integrals. So x to the third over 3 plus a constant. So this just ends up being 7/3 x to the third plus a constant. In other words, that derivative will give you 7x squared, right? If you go backwards. This fourth one here, you can split up with a plus or a minus between them as well. You could put a minus there as well. Let me have you add in this one as well. The integral of a to the x is 1 over the natural log of a to the x plus a constant. Okay. This I'm going to do with u substitution. All these I'm going to do with u substitution. Okay. So we'll get to those. But let's go ahead and practice some of these here. All right, find the antiderivative for the function. So let's take the antiderivative of 4x cubed. I can put that 4 out front. And then I can just run the rule. So 4 stays there. Run the rule. X to the 3 plus 1 over 3 plus 1. Don't forget plus the constant. So this just ends up being x to the 4th plus a constant. And here you notice it says let c be 0. So we're just going to end it with x to the 4th. But that could be any number, right? That c could be any number. Let's do it for, what if you have a negative exponent? So x to the negative 8 plus 1 over negative 8 plus 1 plus a constant. So that would be x to the negative 7 over negative 7 plus a constant. In other words, negative 1 over x to the 7th plus a constant. Whoops, I just realized I did not get that in there. Thank you, Julian, pointing that out. Maybe that's 1 over negative 7, which is negative 1/7. My goodness. All right, let's keep going here and find this antiderivative. We've got the 10th root of x. I'm going to write that in exponential form, so that's x to the 1/10 plus 1 over the 10th root of x. So I'm going to write that as x to the negative 1/10. And then I'm going to take the derivative there. Okay? And so we've got x to the 1/10 plus 1, so that's 11/10 all over 11/10 plus x to the negative 1/10 plus 1, x to the 9/10 all over 9/10, and this is plus a constant. Well, I'm dividing by a fraction, so I'm going to multiply by the reciprocal, so times it by 10 over 11, 10 over 11, right? So we have 10/11 x to the 11/10 plus 9/10 x to the 9/10 plus a constant. 10/9. Oh my goodness. 10/9. Flip that. X to the 9/10 plus a constant. All right, how about the integral? Here we have the antiderivative of sine of 12x plus cosine of 12x dx. Okay, so I'm going to split this up into the sine of 12x plus the integral of the cosine of 12x dx. Now, what I like to do in this section is I actually will introduce u substitution. We're going to do more u substitution in detail in a future section, but it is very nice to use in this section because if you can just remember that the integral of the sine is negative cosine, and I also want you to keep in mind the integral of the cosine is just sine. And remember, if you go backwards, right, the derivative of the sine is just the cosine. The derivative of negative cosine is negative cosine, which is just the sine, right? So that's why those are what they are. And let's use this top one. Integral of the sine is negative cosine. So I have, notice over here, I have sine of 12x. I don't have sine of x, I have sine of 12x. So what I'm going to do is, I'm going to let u be 12x. And so du dx, I'm going to take that derivative on both sides, is 12. And then what I'm going to do is, I'm going to take the dx to the other side. Okay, so I have du is 12 dx. And let me actually erase this other stuff right here. Okay, so u is 12x, du is 12, the derivative dx. So I'm trying to get this in the form of sine of u du. So notice I gave this the name u, 12x is u. And du, see how du is 12 dx? Well, I have a dx, I just need a 12. So if I put a 12 in, I have 12 dx, but I got to offset the 12. So I give it 1/12, because 1/12 times 12 is 1. So I haven't changed it, right? And let's go ahead and fill this in. So I have 1/12, the integral of the sine of u du. Remember, du is 12 dx, du. Okay? And so this just ends up being 1/12. 1/12 stays there. I know the integral of the sine is negative cosine of the u. Now I am going to plug in the u though. I got to plug that u in at the end. So this will be negative 1/12 cosine. What's our u? 12x. Plus, now let's do the next one. This one I don't have cosine of x dx, I have cosine 12x. So again, I'm going to let u be the 12x again. So my du dx is 12. In other words, du is 12 dx. I don't have a 12. Now I have a 12 dx. I got to offset it with a 1/12. So this becomes 1/12 integral of the cosine of u du. So we got 1/12. The integral of the cosine is just the sine. So it's the sine of u. And then we got the plus c on the end. So this is 1/12. Put the u back in. And there we are. That's called u substitution. Okay. All right, this next one we've got the antiderivative of negative cosecant squared 2x over 5 dx. And so you can just look at, I have a little copy of my sheet here. All right, if you look at your thing, I'm like, oh, well, I know the integral of the cosecant squared is no negative cotangent of u plus c. Let me come back to this. So let me make a note of that. The integral of the cosecant squared is negative cotangent of u plus c. Okay. Well, I can push the negative out, but I still have this 2/5 x. That's my u. So I'm going to have to let u be that 2/5 x to do this. So let's let u be that 2/5 x. So du dx would be 2/5. In other words, du, take the dx to the other side, is 2/5 dx. Well, I have the dx. I'm missing the 2/5 part again. So I put in the 2/5, give it a 2/5. Now I have 2/5 dx. Offset it with 5/2 out front, right? Multiply by the reciprocal. Because 2/5 times 5/2 is just 1. I'm just multiplying this thing by 1. And now let's see what we have. I got negative 5/2 integral. Here's my du, right? And I've got this cosecant squared of u. And we run it. Negative 5/2 stays there. The integral of the cosecant squared is negative cotangent of u plus c. So this, a negative times a negative, is a positive. Put the u in now. The u is the 2/5 x, or 2x over 5. And there we are, 5/2 cotangent of 2x over 5 plus your constant. If you notice on this, you can see how you got that x, and this is a typo. That's actually supposed to have a 13 right there. So let me rewrite this. I'm finding the antiderivative of 1 over 13x, square root of 169x squared. Let me write that as 13x quantity squared minus 1. Hopes that you can see that u there. So what I'm looking for is, on my sheet, let me pull up my sheet now, a 1 over u square root of u squared minus, hopefully you can see it right here. See that? That's the one we're going to use. Now a is just a number. That's a constant squared right there. In this case, we had a minus 1 squared right there, so the a is the 1. Okay, so that's what we're using. Let me come back and write that down. So we have the integral of 1 over u, it was the square root of u squared minus a squared, is 1 over a arcsecant of u, absolute value of u, over a plus a constant. Okay. So can you see, hopefully you can see how the u here, here's my u, here's my u. My u is 13x. So this is in the form, it fits the form, if you will, right? And my a is the 1, right? This is like 1 square, so my a is 1. So u is 13, a is 1. So it gives it to us. So this is 1 over a is 1, arcsecant of the absolute value at the 13x. We're just going to assume that that's positive right away, 13x there, over a, which is 1, plus our constant. Oops, I had an a right there. That's supposed to be a 1. My a is 1. So we just have the arcsecant of 13x plus a constant. And again, you can assume that's positive. That's fine. All right, on this one, I'm going to use the integral of a to the x is 1 over ln a times a to the x plus a constant. Okay, so you get this 1 over ln a thing going on. Well, I don't have, here I have, well, let me write it. E to the 3x minus e to the x over 7 minus 1 over x dx. Okay. Now the other one I should give you is the integral of 1 over x is the natural log of x plus a constant. So there's another formula that we'll want to use here on that last piece there. Okay, so I'm going to split these up. Integral of e to the 3x minus integral of e, I'm going to write that as 1/7 x minus integral of, and these are all with respect to x, minus 1 over x dx. Now see how I'm using I'm taking the integral of e to the u, so I'm going to use this. It's just like a to the x, right? It's that same formula there. Now the problem is I don't have just an x up there, I have 3x. So I got to let u be the 3x. So du is 3 dx. So I put a 3 there, I offset it with a 1/3. So I have 1/3 integral of e to the u. Remember 3 dx. 3 dx is du. Let me just finish that piece of it. So that'll be 1/3. And now I'm running the formula. The integral of e to the u, or a to the x, is 1 over ln of e. E to the u, a to the x, plus a constant. We'll get the plus constant at the end of this. Well, ln of e is just 1. That's 1/3 times 1 over 1. So I have 1/3 e to the u. Our u is 3x. Okay? Minus. Now we're going to do the rest of this. Minus. Now we've got to do it for e to the 1/7 x. So this time we're going to let u be the 1/7 x. So let u be the 1/7 x. So du is 1/7 dx. So I need a 1/7, and I got to offset the 1/7 with 7 over 1. So this will be minus 7 integral of e to the u du. So we got minus 7. Now I run the integral of e to the u. That's 1 over ln of e to the u. And we'll do that part of it in just a second. So minus 7. Natural log of e is just 1. And so we got 1 over 1, and we got e to the u. Well, e to the u is 1/7 x. Now let's finish the last one. Minus the integral of 1 over x, natural log of x. Don't forget the plus constant. Let's keep going. Notice here we can just run that power rule, right? X to the n dx is x to the n plus 1 all over n plus 1 plus a constant. So I'm going to do that. 4 stays there. X to the 3 plus 1 is 4 all over that 4. Plus 6 to the 2 plus 1 is 3 all over that 3. Minus, and the integral of k dx is just kx plus a constant. So minus 3x. Plus a constant. So we got x to the 4th plus 2x to the 3rd minus 3x plus our constant. All right, this next one I'm going to go ahead and put into exponential notation. So I'm going to write it as 3x negative 2 minus a 1/5 x to the negative a half plus a 3/4, all with respect to x. So 3 stays there. X to the negative 2 plus 1 is a negative 1. Minus 1/5 stays there. Negative a half plus 1 is a 1/2, positive 1/2, that's all over the 1/2, and then throw an x on, kx, right? So we got negative 3 over x. I'm going to this is dividing it by a half, so times 2 over 1 times 2 over 1 right there. So minus 2/5 square root of x to the 1/2, plus 3/4 x, and then plus a constant. Here I would go ahead and rewrite this. I'm going to distribute that, so I have x to the negative 3 plus 1, so I get x to the negative 2. X to the negative 3 times the positive 1 is just x to the negative 3. And then I've got this sign of 3x dx. And let me go ahead and write that. These two I can just run with my power rule. But over here I'm going to have to use u substitution with that sign of 3x. So let's go ahead and finish these two. Negative 2 plus 1 is a negative 1. Negative 3 plus 1 is a negative 2. And then here I'm thinking to myself, well, I know the integral of the sine is negative cosine. Because remember, the derivative of negative cosine will get you back to just sine, right? And so that's what I'm going to use here. I'm going to say, well, that's got to be my u. U's got to be the 3x. So du is 3 dx. So 3 dx, I got to offset it to the 1/3, right? So I have 1/3 integral of sine of u. Here's my du. And so I got 1/3 integral of sine is negative cosine of u. U is 3x. And then plus the constant. Let's clean this up. I got negative 1 over x minus 1. Whoops, I missed that. Negative 1 over 2x squared minus 1/3 cosine 3x plus a constant. All right, here this next one, I'm going to go ahead and I'm going to write this as 5e to the negative 2x plus 3 to the 4x dx. And I'm going to go ahead and split these as well. Okay, and I'm using this, the integral of a to the x, or a. I'll do it with u here. A to the u. Oh my goodness. A to the u du is 1 over ln of a to the u plus a constant. So that's the one on my sheet that I'm using. And so I'm going to push this 5 out. And I'm going to let that u be that negative 2x. So I'm going to let u be negative, let's see, I'm not going to have room there. Let me just do it below. Let u be negative 2x. So du dx is negative 2. Let's take the dx to the other side. So negative 2 dx. I need a negative 2. Give it a negative 2. Now I got negative 2 dx in there. Offset it. Negative 1/2. Because negative 1/2 times negative 2 is a positive 1. Right? So what I have now is I got this negative 5/2. And I got e to the u. And there's my du. Negative 2 dx. So I can run my rule now. Right? Let's go over here and let's also do, let's let u be the 4x. So du would be 4 dx, so offset of the 1/4. And so we've got plus 1/4, 3 to the u du. And so we have negative 5/2. The integral of e to the u is 1 over ln of e to the u, which in this case the u is negative 2x, plus 1/4, 1 over ln of 3, 3 to the u, but in this case the u was 4x. Remember, ln of e is 1, so I got negative 5 halves e to the negative 2x. Let me just take that actually down to the bottom. So I get negative 5 over 2e to the 2x plus 1 over 4 ln of 3 times 3 to the 4x plus a constant. And I could write this, that's the same as 3 to the 4th to the x. So you could also write this as 3 to the 4th is 81 to the x over 4 ln of 3. This is the same thing. 3 to the 4x is 3 to the 4th to the x, power of a power. All right, on this next one, notice you're dividing everything by that x squared. So I would take that x root x over x squared. I would take the 2/3 root of x over x squared minus x over x squared. And let me rewrite that as x times x to the 1/2 is x to the 3/2 over x squared plus 2x to the 1/3 over x squared minus x over x squared. And so what you have here is 3/2 minus 2, right? I'm using this rule. It's a to the m minus n, right? So we got x to the 3/2 minus 2, which is x to the negative 1/2, right? 3 over 2 minus 4 over 2. Plus 2x to the 1/3 minus 2. That's a negative 5/3. And then one of these x's cancels, minus 1 over x dx. First two I can run the power rule. I'm going to go ahead and make that its own separate because I know the integral of 1 over x dx is the natural log. Okay, so this one will be minus an ln of x right there. Plus a constant. These ones are power rules. So x to the negative 1/2 plus 1, 1/2. All over 1/2. Plus 2 stays there. Negative 5/3 plus 1 is a negative 2/3. All over negative 2/3. So this becomes 2 square root of x, x to the 1/2. And then 2 divided by negative 2/3 is 2 times 3 is 6, negative 6/4. Or negative 2, hold on, 2 divided by negative 2/3, negative 3 over 2, oh yeah, negative 3, sorry, minus 3 x to the negative 2/3, so that's down there, minus the natural log of x, plus our constant. All right, here this next one I'm going to split it up as theta being squared d theta plus the integral of secant squared. And so I'm looking on my formula sheet, I would find the integral of the secant squared. And the integral of the secant squared du is just tangent. Because remember the derivative of the tangent, secant squared, remember that? So the integral of secant squared would give us tangent, right? So I'm going to have to let my u be that 7 theta. So my du is 7 d theta. Put a 7 in, offset it with a 1/7. So you've got the integral of theta squared. I'll just use the power rule there, plus 1/7. The integral of secant squared of u. And here's my du. Right? And now let's run it. Theta to the 3rd over 3 plus 1/7. The integral of secant squared is just the tangent of u. U is 7 theta plus a constant. So we got theta to the 3rd over 3 plus 1/7. Tangent is 7 theta plus a constant on that. All right, let's keep going here. I'm going to rewrite this. You remember how sine squared plus cosine squared is 1, right? So 1 minus cosine squared is sine squared. So I could rewrite this as the cosine of 4 theta over sine squared of 4 theta d theta fact, let me rewrite that as that's 1 over sine of 4 theta times cosine 4 theta over sine 4 theta d theta. And then I'm going to rewrite that. That is cosecant of 4 theta and cosine over sine cotangent 4 theta. So I did all that rewriting because on my formula sheet I have the integral of the cosecant of u cotangent of u, and its integral is just negative cosecant of u. Okay, so that's where I was trying to get to on this one. It's the integral of cosecant cotangent, right? Which I did. And notice my u here, my u would have to be the 4 theta. So du would be 4 d theta. So I just need to give it a 4 and offset it with a 1/4. So I have 1/4 the integral of the cosecant of u cotangent of u du, because du is 4 d theta, right? And so this ends up equaling 1/4. The integral of the cosecant cotangent is negative cosecant of u. Well, our u is 4 theta. So this finally just ends up being negative 1/4 cosecant of that 4 theta plus a constant. Okay. This next one I have the integral of 1 over 1. Let me rewrite that as 2x being squared. That's the same as, and so I'm looking on my formula sheet. I'm looking for like 1 over a squared plus u squared du. And I find on my formula sheet that it gives me that is 1 over a, and it's the arctangent of u over a plus a constant. And so our u here, see how our u is that 2x, and our a is 1. So u is 2x, a is just that 1 right there. 1 squared is 1, right? And so I could just follow this real easy. So it's 1 over a arctangent of u over a plus constant. So this just ends up being the arctangent of 2x plus a constant. Oh my goodness, I'm so sorry. I messed this up. My u is 2x here. I do have to account for my 2x. My apologies on this. My u is 2x, so my du is 2 dx. I forgot to put that in. 2 dx. I got to offset it with a 1/2 out front. There we go. So we got 1/2 arctangent of 2x plus c, right? All right, let's do our first initial value problem. I got dy dx is 6x squared. So what I'm going to do is I'm going to try to get back to the original function and figure out what the constant is from that point that they give you 0, -1. Okay. So what I'm going to do is I'm going to take the dx to the other side. And now I'm going to run the integral. Well, the integral of 1 with respect to y is 1y. Now, I know it's plus a constant, but I have a constant on the other side, so I don't have to worry about it. So I'm going to just put the plus c on this right-hand side when I do this. So let's go ahead and run it over here, 6x to the third over 3, and there's my plus c, right? I only need to put the plus c on one side here. So here's our function in terms of x. Y of x equals 2x cubed plus a constant. Now, I got to use the given right here. So I'm going to use y of 0 is -1. So here's what we have. We have y of x is 2x cubed plus a constant. Throw the 0 in. And remember, y of 0 is -1. looks like our constant's -1. So now I can go back and I can say, oh, well, since y of x equals 2x cubed plus c, then our c must have been -1. So the initial, or the original function was 2x cubed minus 1. So in other words, this is saying, let me give you a picture of this. This was 2x cubed minus 1, and its derivative is 6x squared, but this is the only function that goes through 0, -1. So I had to know that my constant was -1, right? Because all these 2x cubed, I could have 2x cubed plus 2 or 2x cubed plus 4, whatever. All of their derivatives are still 6x squared, but there's only one of them that goes through that 0, -1. So you had to find that one. Let's do another one, except with a second derivative. So let me give it to you with this notation. My second derivative here is x squared. Let's go ahead and take the antiderivative. So that'll get us back to the first derivative, or I'm sorry, let me do y, not f, as y. So that'll get us back to the first derivative. Now let me run the integral over here, the antiderivative. So I have x to the third over 3 plus a constant. Now let me use the fact that y prime of 0 equals 6. Y prime of 0 is 6. So 6 is our constant. So y prime of x is x cubed over 3 plus the constant, which is 6. Now I have the first derivative with my constant. So let me come up here. Let's take the integral of that now. So I'm going to run the integral now of that, which will give me back to the original y of x. The 1/3 stays there. X to the 4 over 4 plus 6x plus a constant. So it looks like the original function is x to the 4th over 12 plus 6x plus a constant. But I got to use the fact that y of 0 is 3. Y of 0 is 3. So 0. So it looks like my constant is 3 when I plug that in. So y of x is x to the 4th over 12 plus 6x plus that constant, which is 3. Do one more of the trig function here. I've got d squared r over d theta squared. So the second derivative of r with respect to theta, I'll write it this way, is the sine of 5 theta. So I'm going to go ahead and take the antiderivative. That'll give us the first derivative. And now I know, keep in mind that the integral of the sine of u is negative cosine of u plus a constant. So I've got to let u be the 5 theta. See, du is 5 d theta. Give it a 5, offset it with a 1/5. So I got a 1/5 the integral of the sine of u du. So r prime of theta is 1/5. The integral of the sine is negative cosine of u is 5 theta, plus a constant. So r prime of theta is negative 1/5 cosine of 5 theta plus a constant. Now I got to use, so that's step 1. But I got to use the r prime of 0 equals 1. So r prime of 0 is 1. Cosine of 0 is 1. So add 1/5 to both sides. It looks like our constant ends up being 6/5. So let me come over here. So we know r prime of theta is negative 1/5 cosine 5 theta plus the constant, and our constant is 6/5. And now we're going to integrate that so we can get back to just r of theta. And I'm going to do this separately. Okay. So I'm going to have negative 1/5. I'm going to have to let u be that 5 theta. So I need 5 d theta. 5, which means I got to offset it with a 1/5. So it looks like now I got negative 1 over 25, the integral of the cosine of u du, plus, I'm going to go ahead and just take that derivative, antiderivative, 6/5 theta plus a constant. And the integral of the cosine is just sine. So this is negative 1/25. The integral of the cosine is just the sine of u. Well, our u is 5 theta. So we got negative 1/25 sine of 5 theta plus 6/5 theta plus a constant. That's r of theta. Now we're going to use that r of 0 equals 6 right there. R of 0 equals 6. So let's plug it in. R of 0 is 6. Negative 1/25. 0 is going in for theta. Sine of 0 is 0, so that's gone. 6/5 times 0 is gone. So it looks like our constant ends up being 6. So r of theta is negative 1/25 sine of 5 theta plus 6/5 theta plus 6. Thanks so much for watching. I hope that helps you get started.